In this video, we discuss learning outcome number 4 from lesson 8.1, which is about testing a claim about a population proportion using the critical value method. Now, the process starts exactly the same way whether you're talking about the critical value method or the p-value method. We're going to start by writing the claim in symbolic form and then using that to infer the null and alternative hypotheses. Then we're going to either identify the sample statistic in the problem statement or compute the sample statistic and identify the sample size n. And then we want to graph a sampling distribution of that sample statistic, assuming that the null hypothesis is true. So that's going to give us the mean of that sampling distribution. And then we want to label the value of that sample statistic from our sample on that graph. And the question becomes, is the value of the sample statistic from our sample extreme or extremely rare or just very unlikely to occur given that the null hypothesis is true? If it is unlikely to occur, we'll say the null hypothesis must be false. If it's likely to occur, we'll say, there's not enough evidence to get rid of the null hypothesis. Okay, so in order to do that, we need to go from that sampling distribution of the sample statistic to a corresponding distribution whose areas we know. So to do that, we always go from our sample statistic to a test statistic corresponding to that sample statistic. So you're going to use a z-score when appropriate, a t-score, or a chi-squared value, depending on the type of problem that you're working on. And then here is where we get into the critical value method. I'm going to outline it for you, then I'm going to define a few terms, and then we'll go back to this list, and then we'll actually apply it in a particular example. So here is the critical value method for testing a hypothesis. We're going to use this to make a decision about the null. The first thing that we need to do with the critical value method is determine whether the test is two-tailed, left-tailed, or right-tailed. And then we're going to want to sketch and shade the critical region on the distribution corresponding to our sampling distribution of that sample statistic. And then we want to find the critical values after that conversion to the new distribution. And then we're going to use the critical values and the test statistic to make a decision. We're going to say that if this test statistic, lies in the critical region, then it corresponds to a value of the sample statistic that is significantly high or significantly low. So we know that's very rare that that's happening, but it's supposed to be rare that that's happening, but it's actually happening. And therefore, maybe our assumption was false, so we should reject the null hypothesis. Again, that's the rare event rule for inferential statistics. Or if the sample statistic does not lie in the critical region, we'll say, well, the value of the sample statistic is likely to occur given our assumption. So we don't have enough evidence to reject the assumption. Then finally, we state our conclusion about the original claim in non-technical terms. So let's talk about the critical region and the critical values. After computing the test statistic, which we talked about in the last video, we need to decide if the test is two-tailed, right-tailed, or left-tailed. We'll get to that in a moment. Then we need to sketch the critical region and find the critical values. Now, the critical region is also known as the rejection region. This is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. And again, remember the test statistic corresponds to a particular sample statistic. So this is just like a normalized version of that distribution for the sampling distribution that we started with. So if your sampling distribution was approximately normal, but it was a non-standard normal distribution, we standardize it, and we go to the standard normal distribution and look at those graphs instead. But the areas correspond in a way that's just one-to-one. The area over in the standard normal distribution corresponds to the area corresponding to that cutoff of the test statistic and the sample statistic in the original sampling distribution. Okay, so the critical region is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. And this could be in the tail, the left tail, the right tail, or in both tails. And a critical value is just a value separating those values of the sample statistic that are typical, given that the null is true, from those that are significantly high or significantly low. So here's a picture Now remember, the critical region is going to have area alpha. Alpha is the significance level for our test. Now in a two-tailed test, usually, every time in that case, our null hypothesis will say that some parameter is equal to a value. In a two-tailed test, the alternative hypothesis says a parameter is not equal to a value. We're going to say, we don't care if it's too high or if it's too low. We're just going to say that it's not equal to that value. In that case, we're going to do a two-tailed test. And that means that alpha area is split into two tails. So we're going to have half of alpha in this tail and half of alpha in that tail. Now for a left-tailed test, or we will have a left-tailed test whenever that alternative hypothesis includes this less than sign. See that right there, the less than sign? Notice that that arrow, if you think of that less than sign as an arrow, it points to the left. So that points to the left tail. So this is a left-tailed test, and the less than arrow points to the left. So it points toward the tail. So this is going to be a left-tailed test in that case. And then we have a right-tailed test if our alternative hypothesis includes a greater than sign. So we'll say our parameter is greater than some value. Again, that arrow points in the direction of the tail. So if you see that greater than sign, it's pointing to the right. That means we're interested in the area to the right. Now, both for the left-tailed test and the right-tailed test, the area in that left tail or right tail is alpha. Only in the two-tailed test do we take alpha and split it into two pieces. So we've got alpha over 2 area in this region and alpha over 2 area in this region. So those are the left-tailed, right-tailed, and two-tailed tests. These green regions in every picture are called critical regions. So this is a critical region. There we go. So this is a critical region, and that's a critical region. In the left-tailed test, the far left tail is our critical region, and a right-tailed test, that far right tail is our critical region. And the critical value is the value that separates the area in those tails from the rest of the area. So we're going to say that a value of a sample statistic is significantly high or significantly low if it corresponds to values of the test statistic that are in these critical regions. So a value of the test statistic that is significantly high or low would occur in the left tail or right tail, or one that is significantly low for a left-tailed test would occur in that left tail, and that would cause us to reject the null hypothesis. And then over here, we'd say it's significantly high if our z-score or our test statistic lied in this right tail. But again, the z-score that separates that area where we've got test statistics that are significantly high or significantly low in the tails, and then those that are typical sort of in the middle in this yellow area, the z-score or the t-score or the chi-squared value that separates those is called the test statistic corresponding to that particular test. Oh, I'm sorry, I said that wrong. That's the critical value corresponding to that particular test. So the cutoff values are the critical values. The test statistic is the value of z or t or chi-squared that corresponds to the sample statistic that you started with. Okay, so again, we have to determine whether the test is one-tailed or left-tailed, right-tailed, or two-tailed. We want to sketch and shade the critical region. We want to find the critical values. So that is that cutoff value that separates significantly high or low values from the rest of the values. And then we want to make a decision. If the test statistic lies in the critical region, so that means the test statistic is more extreme than the critical value, then we're going to say that that test statistic corresponds to a sample statistic that is significantly high or significantly low, given our null hypothesis being true. Then we're going to say, well, if this value is significantly high or low, that means it's very improbable, given that our null hypothesis is true. So we're going to say, since it's improbable that it should happen, but it's happening, the null hypothesis must be wrong. So we'll reject the null. Now, if the test statistic does not lie in the critical region, the value of the sample statistic in that case is likely to occur given our assumption. So in that case, we fail to reject the null. And then we state a conclusion about the original claim in non-technical terms. That's how we finish up our hypothesis test every time. So let's go back to our personal online data example. This time, we are conducting a hypothesis test using the critical value method, and the significance level that I've given you is alpha equals 0.025. So the first thing that we need to do every time you conduct one of these tests is state the original claim. Now, let's see, the original claim is right here. It says most adults would erase all of their personal online information if they could. Most adults means that the proportion is greater than 50%, or the percentage is greater than 50%, which means the proportion is greater than 0.5 if we're thinking of that in decimal form rather than percentage form. Sorry about that. Have trouble with the annotations tonight for some reason. My computer's being a little buggy. Okay, so the original claim is that P, the population proportion, is greater than 0.5. And then we say, well, what's true if that's not true? Well, then P would have to be less than or equal to 0.5. And then we look at those two statements and we say, which one does not contain the condition of equality? And that, in this case, happens to be the original claim. P is greater than 0.5. And then we say, okay, that's the alternative hypothesis. The null hypothesis always includes an equal sign, not a less than or equal to sign. So in this case, the null is that the population proportion is 0.5. You say, okay, I stated my claim, I identified the null and alternative hypotheses, and then I want to say, okay, assuming that that population proportion is 0.5, how rare is it to get a sample proportion like the one that we had in the problem statement? Well, the one that we had in the problem statement was that 59% of the 565 randomly selected adults said that they would erase all of their personal information online if they could. 59% corresponds to a sample proportion of 0.59. And the sample size associated with that is 565. So I would take this information, I would graph the sampling distribution of the sample proportions. That's what this graph is over here. And I would say, well, under most conditions, though, that is approximately normally distributed. And the mean of the sample proportions is the population proportion, because the sample proportions are an unbiased estimator of the population proportion. So we're going to, if we're assuming that the null hypothesis is true, so that the true population proportion is 0.5, well, that's going to be the mean of the sampling distribution of sample proportions. Okay, so we're saying these are sample proportions, the mean is P equals 0.5. And then we're saying, okay, well, where is P hat equals 0.59 relative to 0.5? Well, I know it's farther to the right. And we remember from earlier examples, other videos, that it's this graph is not accurate. This graph seems to imply that P hat equals 0.59 is about, this is 0 standard deviations from the mean, that's 1 standard deviation, that's 2 standard deviations. So from this picture, it looks like P hat equals 0.59 is about 1.4 standard deviations above the mean. The picture is completely wrong. Whenever I do this, I'm just sort of graphing a cartoon and I'm like, it's greater than the mean, so it's to the right. And it just helps me visualize what's going on. But I actually don't know how many standard deviations until I calculate the test statistic. So we do all that. We graph it to visualize what's happening. And then I say, okay, how high is that P hat? How extreme is that P hat if the population proportion is 0.5? Well, that requires calculating the test statistic. We did this in another video as well. Now, the test statistic for population proportions, or excuse me, sample proportions, is a z-score, because sample proportions are approximately normally distributed. So remember way, way back when we first started computing z-scores, we said, let's take x, subtract the mean, divide by the standard deviation. That's exactly what we're doing here, but instead of x being our random variable, now p hat, the sample proportion, is our random variable. So we've got p hat here, and then we're subtracting the mean of the sample proportions. And we're assuming that the mean of the sample proportions is the value of p in the null hypothesis. And then we're dividing by the standard deviation of the sample proportions, which is approximated by the square root of p times q over n. Given that our sampling distribution of sample proportions has a mean of 0.5, which means that the true population proportion is 0.5. So we plug everything in. I've got 0.59, that's the sample proportion from my sample. I'm subtracting the 0.5, that's the population proportion in my null hypothesis. And then I divide by the square root of p times q over n. P was 0.5, q is the complement of that. So I do 1 minus p to get q. In this case, the complement of 0.5 is 0.5, and then you just do the arithmetic. Now, what I would recommend you do if you're doing this at home is I would use your calculator, and I would do that denominator first, and then do the numerator divided by the answer. So I would type 0.5 times 0.5 divided by 565, hit enter, hit square root of the answer, hit enter, and then type the numerator divided by answer and hit enter in order to get that 4.29. There is another video in which we compute test statistics, and I actually do that on my calculator for you. I highly recommend that you check those out so that you can see how you enter it into your calculator. And many students will have the right value on their piece of paper, but perhaps type it into the calculator incorrectly because of order of operations, missing parentheses and things like that, and not get the right answer out of the calculator. Okay, so check those videos out if you need to. That will give us our test statistic of 4.29. Now remember what that means. It means that this value of p hat being 0.59, it's actually not this what looks like 1.4 standard deviations above the mean, given that the population proportion is 0.5. It's actually 4.29 standard deviations above the mean. 4.29 standard deviations above the mean for a standard normal distribution is extremely rare, very rare. So I think we're going to reject the null, but let's do the rest of our test. Okay, so we compute the test statistic, and we're going to use a critical value method now to do this hypothesis test. So the next thing we do is determine whether the test is left-tailed, right-tailed, or two-tailed. We know that p was greater than 0.5 in the alternative hypothesis. So that means our test is right-tailed because that arrow points to the right. Then we want to identify alpha, sketch the critical region, and find the critical value. Our significance level of alpha equals 0.025 was given to us in the problem statement. And the critical z value associated with that area is z sub 0.025. If you look up the area of 0.025 to the right, or alternatively, the area to the left of 0.975, because this is saying we want let's look at the picture. We want the area of the top 2.5% to be our critical region. Well, that means the bottom, the rest of the area, if this is the top 2.5%, the rest of the area must be the bottom 97.5% of the area, or 0.975 is our area over there. So we've got that, we've got this area to the right of 0.025, and then you go to the table and you look up the area to the left of 0.975. When you do that, you find that the corresponding z value is z equals 1.96. That's our critical value. So that separates values of the test statistic that are sort of typical, and those also correspond to values of the sample statistic, the sample proportions that are sort of typical, from those that are significantly high. And when we say significantly high, we mean values of that sample statistic or the sample proportion that are in that top 2.5% of values given that the true population mean is 0.5. Okay, so now we take that graph and we graph the test statistic, that 4.29 standard deviations above the mean, and we make a decision. Now, the critical z-value is 1.96, and our test statistic z equals 4.29. That's 4 standard deviations above the mean. This is 1 standard deviation, 2 standard deviations, 3 standard deviations. 4 would be here, and 5 would be after that. So this 4.29 is in between the 4 and the 5. It's way out there. Since this test statistic is way out in this critical region, it's way out in the tail, far beyond that critical value of z, we're going to reject the null. We're going to say that's definitely significantly high. So that's one way to use the critical value method, is to just graph it and look at that z-test. If it's in the critical region, reject the null. Or another way to do it, and I think this way is in your book as well, is to look at the absolute value of z-test and compare it to the absolute value of z-critical. If the absolute value of z-test, which is 4.29 in our case, is greater than the absolute value of z-critical, which is 1.96, what that's saying is that that z-test score is much more extreme than that critical value of z. So it's farther out in the tails. And in that case, we're going to reject the null hypothesis. Okay, so now after all of that, you have to make some conclusion. And so we're going to say that sample evidence suggests that we should reject the null. So the true population proportion is not 0.5. And that supports the claim that p is greater than 0.5. Or alternatively, rather than saying it in terms of p, let's talk about the original claim. The original claim was that most people would erase their online data if they could. What we've just shown is that evidence suggests that the idea that the population proportion is exactly half. So half would erase their online data if they could, the other half wouldn't. That idea is very likely to be wrong. How likely? Well, it's likely with a significance of 2.5% or 0.025. I hope that helps. I hope that helps you understand how this works. I'll see you in the next video to talk about the p-value method, which is a very similar method. It just, instead of looking at values of the test statistic and values of a critical z-value and then comparing them, or looking at a critical region and comparing whether that test statistic z is in the critical region or not, rather than doing that, we're not going to compare z values and see if the z is in a critical region. We're going to compare probabilities, so actual areas under the curve. We're going to say if our probability p, capital P, is less than or equal to alpha, which is our significance level, well then that probability indicates that that event happening, that occurrence of the sample statistic just appearing whenever we do our calculation, like that's extremely rare. So it's giving us a probability, and we're saying that that's extremely rare that happens, given that the null hypothesis is true, and therefore we should throw it out if p is less than alpha, less than or equal to alpha. If p is greater than alpha, we're going to say, that value of the test statistic is likely to happen due to chance, so we shouldn't reject the null. In that case, we should fail to reject the null. Okay, so that's for the next video. I'll see you next time.